In this video, we're going to take a look at polyatomic ions, which we've bonded before with ionic bonding, but now we're going to look at how the polyatomic ion is actually bonded, the elements that are in that ion, and we're also going to look at some of the exceptions to our octet rule when we are doing molecular formulas. So first of all, we need to remind ourselves that poly means many, so this is a group of atoms, at least two or more, and it has a positive or a negative charge. Most of them are negative, but we do have the one positive one. And it behaves as a unit, so it's one group of atoms, and we can't change the amounts of oxygens or things in them. So if we take a look at ammonium, for example, NH4, and it's the only positive that we had, it has a total of 8 electrons in it. And we know that because if you look at your periodic table, nitrogen has 5 and valence electrons. Each hydrogen has 1, so that would be 9, but yet the positive charge means that it lost 1 electron. So there's where we get our total of 8 electrons. Now, because we have those 8 electrons, this is the way nitrogen is going to look. Nitrogen had 5 of its own, so I'm just going to mark our 5, 1, 2, 3, 4, 5. So let's just say those 5 like originally belonged to nitrogen. Well, each hydrogen would have contributed 1 of its own, but you notice that we have like 1 missing. Like this hydrogen doesn't have 1 of its own originally. So that's where that +1 comes from. We had to lose a electron in order for us to get the 8 electrons, so that we would have this the 8 valence here that we see around our nitrogen sharing with the hydrogens. So that positive is important because it tells us, that we had to lose an electron. So whenever you're doing a polyatomic ion, and you will have some of these to do in a future assignment, you need to make sure that you're putting it in brackets. If it's an ion of any type, you put it in brackets and you put the charge on the outside of it, and that way the person that's looking at it would know that this particular example has the incorrect number of electrons. It either gained or lost based on whatever you tell them the charge is. If we take a look at yet another example, we have SO3 - 2, so sulfite, and normally this would have more electrons than this. We have would have less electrons, we would only have 24. S has 6, oxygen each has 6, so then there's 6 oxygens. So normally we would only have 24 electrons, but this -2 says that we actually have added 2 more electrons to give us our 26 electrons to make this meet the octet rule and everything to have 8. So if you look at how all this is organized, let me erase some of this for you so we can see our oxygens here. We need to have a total of 26 electrons, and so if we count up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25, 26. We have 26 total valence electrons if you were to count up every single dot. Now again, sulfur and the 3 oxygens by themselves would only give you 24, so we need to again have those brackets there with the -2 on the outside that lets the scientists know that we actually had to add 2 more electrons in order for this to work. If we wouldn't have that -2, we would have stopped with just the 24 that we counted, what you see now in the picture. If we would cross these out, we would have 24. And oxygen would have 8 around it, and so oxygens would all meet the octet rule, but sulfur would not. Sulfur would just have the 2, 4, and 6, and so it would be short. And that, again, we want to meet the octet rule, so those 2 extra electrons really are necessary. Now, if we look at some of our exceptions, we do have some, and as you practice, you'll see some more that don't always meet the octet rule. But in general, sometimes there's an odd number. So for example, if you have NO2, NO2 adds up to 17 valence electrons, so there's no way that everything can have an octet when you don't have an even amount. You have to have an even number in order to get those 8. So sometimes that happens. This is the way NO2 would look. You have the 2, 4, remember, every bond counts as 2 electrons because that's what creates a single bond, or a double bond is 4 electrons. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then this extra one here on the nitrogen to make 17. Oxygen has 8, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 around this oxygen, but nitrogen does not. It has 2, 4, 6. It has the 7th one. So there's an exception to our octet rule. Sometimes we have molecules that might have fewer, like in the NO2 example. Sometimes we have some that are more. So boron, for example, here, you can just tell by looking at it that there's only 2 electrons in each of these bonds. So that's only 6 electrons around boron, and it should have 8. So boron is an exception. It can actually have less than. And then we have an example where phosphorus actually has more. Again, counting the bonds, you have 5 bonds, which is going to be 10 total electrons around this phosphorus atom in the middle, which is more than our octet rule. The chlorines would all have 8, and even these fluorines here around boron all have 8. It's usually the center atom that's going to have the issue, having too few or not enough. So some common elements that have fewer: hydrogen, because hydrogen's happy with 2, beryllium with 4, and boron with 6. Those are all really common ones that when you have beryllium or boron, it's definitely okay. If they have less, as far as some that have more than, phosphorus, like in the previous picture, sulfur also can have greater number than the octet. And again, that doesn't happen in every example. There's just certain elements that can bond in a certain way and still be stable enough to exist without deteriorating or breaking down. So those are where we're going to stop with these exceptions, and we'll have some more of those exceptions when we practice the next slide over the VSEPR theory that we will be spending several days on.